So, hi guys. Yes, we're going to use K-Nearest-Neighbours classification technique on the iris data today. The iris data is basically a whole bunch of measurements of the flowers you see in this slide, and we're going to try and predict the species. So we're going to try and predict which species the flowers belong to based on these measured characteristics of the flowers. So here you'll see is just some mandatory introductory stuff we always have to do when we do our work. We have to load our data functions, we have to load the data, which is nice and easy because it's already preloaded into R, and we set our random state. Note that in setting the random state so that other people can replicate our results, that number 2070 is completely arbitrary. As long as someone has your same number, they should get the same results when implementing the same code as you. So you can choose whatever number you want there. Having a look at our data, this is the last 5 observations of our data, and we see some very interesting stuff with this simple function in R. We see that there are 150 observations. We see that there are 4 columns of what we call predictors or features, where these columns measure stuff like the sepal width and petal length and all of that. And then the 5th column is what we actually want to predict, and so that is our species column. When we have a look at some more characteristics of the data with the function summary, most importantly there's all the min and max and mean of all the 4 predictors, but we call them labels. For the last column, the label, we can see that there are 50 of each of these species, and so 50 times 3 is 150. There 150 observations of equal species that we see in the data. When we graph these, and I'd like to point out that this is a very good example of me not doing very well to show you some nice colors and stuff in my graphs, and googling some code and finding this guy having done some nice work on showing the different plots with some nice colors in a graph, and that's what I've incorporated into this presentation. What I'd like to point out is, so these 3 colors represent the 3 different species. When comparing certain features to each other, you can see that there are sometimes very clear distinctions between a species and the 2 other species. Specifically, the red species, which is the Setosa species, looks to be a lot differently characterized compared to the other 2. Here, I'm going to run through this as quick as possible. We're going to split our data into a training and test set, 50-50. The dim function is just checking that we still have 75 observations and our 4 features and a label column. Here we have to slice off our 5th column to create our labels, and you'll see that the class of our labels, the new variable we've created, actually changes from a data frame to a factor because it's only got 1 dimension. But you can use the tail function to see that there are still 5 species. Our data is still there. We haven't lost anything, even though we got this horrible null result. And here we take our original test and training sets, and now we slice off our 5th. We've captured the 5th column in a labels variable and labels variables, but now we actually have to just have the 4 predictors by themselves and not predict with the 5th column, which was what we want to predict. And you can see the class of that as a data frame. This is some horrible maths. The K-Nearest-Neighbours, how it basically works, it's basically a voting mechanism. If you can imagine yourself organized in a class with all your fellow students and being placed in different directions from each other based on your attributes, and then me having to come and not know what, say, your gender is, but there is the closest person to you in the class based on attributes is a male, then I would guess that with 1 nearest neighbors that you are a male. But if I used 3 nearest neighbors, then I would think, well, it's a voting mechanism, equal votes. There are 2 females around you and a male. They're the closest people to you in the data. Then I'm going to vote that you're a female because 66% is the vote for a female. Okay, and there's just the maths. When we finally implement our results, you can see the Setosa, this compares the test labels to what our model predicted. And you can see the model is very good at guessing the Setosa species, whereas there are some odd mishaps in classifications of the Versicolor and Virginica species respectively. So when we increase that to 3 nearest neighbors, you see there still Setosa gets labeled 100% correctly all the time, but there are mislabeled Versicolor and Virginica species according to this model. And there's no difference between the 3 nearest neighbors and 5 nearest neighbors, but there is a difference that is slightly worse because there's an extra observation that is not classified correctly with 1 nearest neighbors. And just a quick point, something you can think about in terms of implementing your models soundly is what would a higher value of K mean? So a higher value of K means we're incorporating more votes, more of these people voting for what this observation is. And that means that actually the function is less flexible because it's going to be averaging over a whole bunch of observations rather than every person, the closest person to them, being allocated 100% the vote of that one person closest to them. Okay.